of 6 minus 6, sinh of 7 minus 7. So it's manifest in that formula that when you put y equals to 1, you get 0, the green one. And I guess it's also fairly clear that when you put y equals to 0, what happens? You get minus sinh plus sinh. There's an extra minus out here. It cancels out. It just collapses back down to 4 cosine 6x. When I put y equal to 0 here, I get sinh of 7 minus 7 over sinh of 7, but that minus also. So we get cosine 7x. So it's pretty easy to see when you plug in y equal to 0, you get back down to the given, which I've erased somehow. Oh, right here in blue, that boundary condition on the edge. It's a little less obvious to me why the, we have the red, the side conditions, but we built those in. They're there too. Just got to look at it long enough, you'll see it. So is the method clear? What do we do? How do you solve a boundary value problem? With homogeneous boundary conditions, you propose that the solution is separable in the sense that it's a product of functions of just one variable. And then you work your way through the boundary conditions. Hopefully you'll find some infinite, series of eigensolutions, as they're called. And then you can apply a Fourier technique to select coefficients in that infinite series of eigensolutions that will fit your problem. And for the problems we're interested in, it works out without further sneaky business. But of course there is, it's really easy to change what we're doing to something that I haven't taught you how to do. For example, what if I said that this was 0 here, but this was 1 over here? If I did that, that would completely stop us in our tracks. That would be an inhomogeneous boundary condition. You need to look at the section in your book which is about that. Yet more tricks are introduced there to solve such a thing. And but anyway, I have more details here. Let's see here. This one, number 3, I also solved in your book. This one actually has a variable. It has f of x instead of, this one had f of x equal to this blue thing. And the second problem is just for an arbitrary f of x. Basically the same song and dance, except what? We're given voltage is 0 on the sides, right? So instead of having cosines, we'll have sines, yeah? But we still get coshs and sinh. Anyway, details. And you'll get to this blank template solution for that problem. And then you actually have to find Fourier coefficients for your given f of x to fit to the a sub n. Then the other boundary condition will link the a sub n's to the b sub n's, and you'll get something like this, where that a sub n is given by this. And so that's kind of a nice problem because it doesn't actually have, it's for a lot of different boundary conditions. You can see how to do it there. Another problem you could solve, well, if you wanted to. I didn't do this to you guys this semester. You can also solve Laplace's equation on a disk. If you change to polar coordinates, the Laplace's equation in polar coordinates. Maybe some of you had Calculus 3 with me. Anybody here have Calculus 3 with me? Ah, yes. Do you remember deriving Laplace's equation in polar coordinates?
I remember polar coordinates.
Ah, okay.
I don't remember details, but I remember doing it.
Ah, yes. This is a problem I sometimes assign, derive that equation in polar coordinates. And, well, you can also do separation of variables for this. Something interesting happens when you do separation of variables into RT. Instead of getting constant coefficient equations both sides, this ends up giving you a Cauchy-Euler problem for the radial function. So here's an example of where a Cauchy-Euler problem comes up in an applied problem. If you try to solve Laplace's equation on a disk, you better be ready to solve Cauchy-Euler problems. And so that's kind of fun. Here's another one of those. Sorry, there's something I'm trying to show you guys. Where the, I have problems with more the word dimensions. I can't find it at the moment. Where'd it go? I wanted to at least show you an example where we had more dimensions. I've lost my example. Oh no. Well, I'll just tell you what happens. If you have Laplace's equation in 3 variables, guess what you do? You assume u is x of x, y of y, z of z. And when you do that, you end up needing not one characteristic value, but 2 characteristic values. But basically the same thing we've been doing goes through. I think if you read section 10.7 in your text, it's got it in there. You have to look at things called double Fourier series, but it's much the same. That actually is not that hard. In my opinion, changing this to a non-homogeneous boundary condition is actually trickier than bumping up a dimension. Well, anyway, guys, so I'm sorry I didn't have pizza today, but I wasn't sure about the rain, and it was just kind of, a little sketchy. So I'm thinking we should have pizza next Tuesday, if that's all right with you guys. I've heard about your many projects. I hear your cry, no class Thursday. If that's okay with you guys? Yes. Okay, yeah. All right, very good. See, I covered the energy analysis earlier, so we're done. That's it. Yeah. I mean, there's always more, but I'll behave.